sound practice problems. So number one, it says, what type of wave is sound? Well, that is a longitudinal wave, as we know. Distinguish between compressions and rarefactions. Remember, this sound wave is a pressure wave in the air. So when air molecules kind of bunch up here and get really close together, that's a compression. When these air molecules get further apart, that would be a rarefaction. And there we have another compression again, and a rarefaction, etc., as the sound wave moves through the air. So again, here would be a compression, and here would be a rarefaction. Number two, range of human hearing is 20 hertz to 20,000. Using speed of sound at 340 meters per second, what are the wavelengths? So actually, how far apart are those compressions in the air? So we go back to our wave equation, which is velocity is frequency times wavelength. So we're going to use 20 hertz first and see what that wavelength is. So we would have 340 meters per second equals 20 hertz times the wavelength. And if I divide 340 by 20, that's going to give me a wavelength of a whopping 17 meters. Right? That's a huge wavelength. That's like double our classroom width. So that's a very long sound wave wavelength, but you can still hear it though, actually. But what if that frequency goes up to 20,000 hertz, like approaching dog whistle frequencies here? So again, we would take 340 meters per second, the velocity equals frequency, this time of 20,000 hertz times wavelength. We do 340 divided by 20,000, we're going to get a wavelength of 0.017 meters, which is actually about 2 centimeters. And again, you can still hear those waves of that frequency. Number three, you wish to produce a sound wave with a wavelength of 1 meter, like our meter stick length. What would its frequency be? Assuming speed of sound is 340. So again, wave equation works for sound waves too. So 340 meters per second. And I want to know what the frequency is of a 1 meter wavelength sound wave. Well, that's obviously going to be 340 hertz if I do the math out. And kind of like just above a middle C, right? Middle C is what, 256 hertz or so? So that's above that. You musician types better know what that frequency is. Number four, what does it mean to say that every object has a natural frequency? Well, that's a frequency things like to vibrate at naturally. So take a glass and just ping it with your finger. It'll vibrate at its natural frequency. Knock on this table. That's the natural frequency of the table in front of me. You can change that natural frequency, but only if you change the physical characteristics of it. So a shorter glass will have a higher frequency than kind of a taller glass, but you need to physically alter that object. Number five, it says Mythbusters. Hopefully you checked out that video on the resonance page in Canvas. But Jamie Bandera shattered that wine glass. The frequency of his voice was at the same frequency as the natural frequency of the glass. And then the other part for resonance is he needed to sing loud enough with enough amplitude or energy to be able to then physically break the glass. So it takes some energy to do that. All right, let's see what else we got here. We got three more, right? We're going. All right, number six. It says piano tuner hears 2 beats per second. That's those woo-woos, woo. When listening to a tuning fork in piano, now he hears 1 beat per second, or she rather says, should she further tighten or loosen the string to make it in tune? Well, if you checked out the tuning the guitar video on the beats page, remember the beat frequency is just the difference between the two frequencies, right? So if I further tighten it, we keep hearing fewer and fewer beats. We heard 2 beats per second, now we only hear 1 beat per second. So we want to keep tightening till we get to 0 beats. That is, when these two numbers are the same frequency, I'll have a beat frequency of 0 and thus be in tune. So similarly with Number 7, two notes are sounding, one's 440, and I hear a beat frequency of 5 hertz. Woo. What are the possible frequencies of the other sound? So this would mean I have a beat frequency of 5 hertz, and one of those is 440 hertz. So I need to figure out what's the other sound that's going to produce beats of 5 hertz with a 440 hertz. So you can see there's two answers here since it's absolute value. So 440 minus 5 is going to be 400, I know I'm writing it backwards, 435 hertz. Or I can go 5 above and 445 hertz. Both of those numbers, if you put them in for F2, will give you a difference of 5 hertz. Oh, and our last one here, number 8. When a sound wave source moves toward an observer, like the ambulance, does the observer hear an increase in wave frequency, wave speed, or both? So remember, we're talking about wave frequency. So when a sound is moving towards you, you're going to hear that frequency increased. When the sound moves away from you, you hear the sound decreased in frequency. The speed is going to be constant. All right, speed of sound in that medium in air is going to be constant. So this phenomenon is called the Doppler effect. All right, guys. Thanks for watching and checking your answers.